Hello, and welcome to the RIT Space Explorations System Acceptance Review for the University Rover Challenge for the 2025 year.
We are a team from Rochester, New York, comprised of 22 members with backgrounds in mechanical, electrical, and software engineering.
We are proud to introduce our first ever submission, the Scorpio Rover.
Our rover features a unique crab suspension system inspired by researchers at ETH Zurich. The mechanical team refined this design over 2 years. It is designed to maintain equal force on each wheel while also maintaining 6 points of contact on the ground. It is designed to traverse all types of terrain from snow to sand to rocky, uneven terrain. Our rover has 6 wheels that have custom 3D printed hubs. We cast urethane tires with a 4-piece split mold over top of these rims. We did this to save weight on each wheel and make them lightweight. The rover has 6 Neo brushless DC motors. We mounted them vertically this year to avoid damage when going over uneven terrain that could hit them. We used custom-made bevel gearboxes to transmit the torque from each motor to the wheels. Our quick swap system features 4 thumb screws. When taken out, this allows us to switch between the modules for life detection, arm, and autonomous missions in under 3 minutes. It uses 3 aviator connectors to quickly connect each module to the rover's electrical system.
We use a Jetson or a Nano to control all subsystems on the rover. This is connected via CAN bus to 3 TNC microprocessors, one for the arm, one for the science module, and one for the chassis, which is mounted to our custom-built main body board. This board has 3 primary functionalities: 1, to regulate temperature on the rover; 2, gather odometry data using our 6-axis IMU; and 3, control all 6 drive motors. This further interfaces with hardware to manage signals on the rover. We have a 2.4 GHz video transmission system that is off the shelf and built for use in an FPV drone. This allows us to transmit video data from the camera mast to the rover during all 4 missions, and we plan to build repeaters for this to increase the range of communication.
Our rover runs on ROS2 to be able to interface between all of its components. Scorpio is equipped with a 3D LiDAR, camera, 6-axis IMU, and differential GPS to be able to complete the autonomous task. All sensor input can be visualized using RViz2. The autonomous algorithm takes input in the form of a GNSS coordinate or camera data. Aruco codes and objects in the field are identified and tracked using OpenCV. The rover calculates the position vector from itself to the navigation goal and derives the necessary velocities to get to the goal as fast as possible. Meanwhile, the LiDAR is continuously searching for obstacles in the way. If there is not a 1.5 meter wide path in front of the rover for 2 meters, a new navigation goal is calculated using the closest clear path. Once this new goal is reached, the rover will then continue to track its primary target.
Our ARM team is partnered with the RIT Multidisciplinary Robotics Club. To maximize the ARM's abilities to complete all the necessary tasks, it features 5 degrees of motion and can be remotely controlled using a Nintendo 64 controller. Carbon fiber supports are used for maximizing axial strength while minimizing weight. To ensure we are able to lift over 5 kilograms, our base, shoulder, and elbow joints are all driven by high-torque brushless harmonic motors. To maximize fine motor control capabilities, our wrist joint features 2 high-precision servo motors. These motors are connected via belts to a bevel gearbox, which actuates our end effector both vertically and rotationally. A high-power servo motor is used on our gripper for clamping onto a variety of objects. The end effector's mechanism, combined with the inverse kinematics we will be implementing, allows us to flip switches and turn knobs with ease. Our gripper also has a solenoid connected to the bottom jaw so that we can press buttons as well as type on a keyboard.
Our science module uses a custom-designed auger with a hardened steel tip for soil collection. We plan to add a spiked probe to our auger that will be pushed into the soil as it plunges. This will measure the subsurface humidity and temperature. As we are collecting soil, our soil splitter divides it into several caches depending on the depth at which it was collected. A small amount of subsurface soil will be stored in a sealed, sterilized container for retrieval later at the base station. From here, a peristaltic pump floods our caches with water to dissolve any minerals of interest. Then, separate pumps send this water up to our detectors. Our primary detector uses loop-mediated isothermal amplification to test for DNA. We use a fluorometer to measure the fluorescence of our samples before and after heat cycling. Our secondary detector is an absorption spectrometer. We measure the absorptions of our samples, then compare them to a database of known minerals to estimate the composition.